Okay, today's video lecture is going to be dedicated to working some examples in radiative transfer for opaque surfaces. So the focus today is going to be on opaque surfaces, not semi-transparent surfaces. And we're going to work a couple of examples while we talk about the core material for Chapter 4 in this. So we start with problem 4.4 from Solar Energy Conversion Systems. This is a radiative exchange problem for two different surfaces. So we have an evacuated tube collector system. This is a solar hot water system. And we're not, at this point in time, we're not assuming that there's a system that's pumping. We're just assuming that it is going to absorb solar light during the day, and it's going to radiate back out long wave light also. So you assume you have an opaque flat plate collector. It could be a tube collector, but let's just look at this as a panel with 2 meters squared of exposed surface absorbing 800 watts per square meter for the net irradiance. We're ultimately going to need to multiply those 2 meters times the 800 to get a balance of Q, of heat transfer, happening in this system. The absorptance of the surface is going to be 0.85, or alpha equal to 0.85, and the air temperature, when I say the temperature of the surroundings, the air temperature is 30 degrees Celsius. If we were to neglect conduction and convection losses and really only focus on radiative transfer, what would the net radiation exchange be between the plate and the surroundings, between the plate and the open air? That's the first question we want. And what would the equilibrium temperature of the collector be given this net gain of energy of 800 watts per square meter? This would be, you can imagine a sunny day at about 10 o'clock in the morning or so. So I'm just underlining a few aspects here. This is an opaque system. It's not transparent. The size of it and the irradiance we're getting. We've got information about the absorptance, alpha, what the surrounding air temperature is. That's going to be important for radiative transfer. And we want to know about the net radiation exchange, Q, as well as the equilibrium temperature of the collector would be. So I'm going to draw a diagram where I'm going to start with surface 1 being this flat plate collector system. So I'm drawing a plate in cross-section. I've numbered it 1. Then I'm going to draw another surface surrounding the plate. And that other surface is effectively air. And I'm going to label that surface 2. Okay, so now I have a radiative exchange between surface 1 and surface 2. And if you've looked at this, you've actually got a special case where we have, that's in our reading, where it's essentially the model of a sphere enclosing a small convex object. So obviously this convex object is the plate, and surface 2, the surrounding air, is in complete communication with surface 1, and so the view factor of 1 to 2, F12, is going to be equal to the view factor of 2 to 1, and that's going to be equal to 1. So this is a special case scenario that we're going to make use of to solve the problem. The special case is special case 2 from our earlier notes. So in comparison, we're going to reflect our general case where Q, the rate of transfer from surface 1 to 2, is going to be the area of the collector times the heat transfer coefficient times the temperature difference between surface 1, the plate, and surface 2, the air. That's equation 4.21. And of course we've got this really dense heat transfer equation. This is how we linearize the heat transfer equation. We actually embedded a very nonlinear equation in the radiative heat transfer coefficient. And obviously that is too complex for what we want to do. We want to make some assumptions that make this problem more tractable so that we can solve the problem. So we're going to make some assumptions that will generate special case number 2. The first of which is that we have a net radiative transfer, which is essentially the same as what we have above. The second is where the assumption comes in, and that's the heat transfer coefficient for this special case surface where F12 is equal to F21 equal to 1. That can be simplified into epsilon of surface 1, or the emittance of surface 1, times the Stefan-Boltzmann constant times the expansion of the temperature. Okay? That's equation 4.26 in your textbook. Okay, so we've been given the absorptance of that solar panel at the temperature of the solar panel, and we can use Kirchhoff's law to find epsilon. So effectively this panel is in thermal equilibrium, and so alpha 1 can be used to find epsilon 1. The temperature of the air was given as 30 degrees Celsius. We'll convert that into Kelvin eventually. And the area of the collector was 2 meters squared. We do not know the temperature of the panel. We know it's in equilibrium, but we don't know the temperature of the panel. And we also do not know the radiative heat transfer coefficient. What we have then is two equations. They are both that are where at least one is nonlinear in nature, and we have two unknowns. Anytime we have two equations and two unknowns, what we're looking for is the use of a parametric solver. And we have just such a solver in Scilab. Almost all engineering programs tend to have these. The code is found in the Design of Solar Energy Conversion Systems webpage. I've actually just grabbed the code out and plugged in snippets of it here. But you can find it right in the webpage. I think it's under F-heat at the bottom of the templates page. So you see here, for the case of radiative transfer with the sky and a flat plate, we're defining two different equations, and those two different equations are in line 2 and 3 of this code. Now clearly I'm using a text editor here because I have line numbers on the left and I've got commenting going out on here, but this is just a snapshot. These two equations are parametric equations of the function that we're defining, fheat.psi. So that this is something that we can run inside of Scilab as a code. Temperature 1 is assigned to the first argument, to the variable heat 1, and the radiative heat transfer is assigned to the second argument, heat 2, in both equations. Now, the reason why I have F1 and F2 as functions is that we are ultimately going to set that left side of the equation to 0, which you're seeing in line 2 and 3, and we're going to solve for those where they intersect each other. So as you read down, you see that I have function 1 has two arguments, both temperature and the heat transfer coefficient, the two unknowns that are mentioned up at the top of the page, and function 2 has the same two unknowns. So two equations, two unknowns. Now line 15 is where we start defining the function. The function is f-heat. The inputs are going to be heat, and it's going to be heat 1 and heat 2 for the two unknowns. And then you see in line 18 and 19 the actual equations written out and ready to go. In line 16, the func proct 0, that's just some basic cleaning up for the equation. It's not fundamental to what we're doing here. And then you see end function that closes out the function f. So we've defined a function with equation set to 0, and now we're going to use the parametric solver in Scilab called fsolve. We are going to save this file as fheat.psi, and we'll solve for those two variables for the fsolve function. We need to put in some knowns though. Oh yeah. That's just connecting the different arguments together in the code for you to look at for later. You can feel free to come back and pause here and just compare code. Okay, we need to put in some knowns, and so I'm going to insert the knowns here. These are, you'll see that continuing on with line 28 and onward, but the code is actually from a different problem. So we're going to need to switch out the area for 2 meters instead of 30. We're going to need to switch out the temperature of the air from ambient temperature to 30 degrees Celsius, convert that to Kelvin, and we're going to need to change the irradiance upon that surface from 900 watts per square meter to 800 watts per square meter. Of course, A is going to drop in as it's defined on line 28. So the process is that we need to solve for the heat transfer coefficient and the temperature of the plate, of the flat plate of the solar collector, using FSolve in Scilab. And then we'll solve for Q12, the net radiative exchange, using our earlier work. So this is still the same code. I've just broke it up into different chunks. And I started on line 36. I'm going to make two educated guesses for FSolve. And they are going to be 300 Kelvin and a radiative heat transfer coefficient of 30. I'm using the F-heat function to solve for that. The output is going to be heat solve. So again, this is some general coding strategies. I encourage you to just use it as a template and modify from there for parametric equation solving. You can look at this further to find out how it's actually working, but first I'd just like you to try it. And the 300 and the 30 aren't magical numbers. They were just educated guesses. Like 300 degrees Kelvin is somewhere at the temperature of the Earth, and 30 is honestly just a number close to what I would expect for heat transfer, but we could probably even put in 300 and 300, and the two numbers would converge because of the manner in which we solve the problems within Scilab. So the output in line 43 and onward is going to be to print out the answer to the screen in Scilab, and it uses formatting parameters of the C language. So you're going to see code for a new line, that's /n in the Scilab. You're going to see the Scilab multiline code, which is basically saying keep reading on to the next line. From 46, keep reading on to 47. From 47, keep reading on to 48. From 48, keep reading on to 49. And you see that it's all from 46 to 49. I'm all encompassing with a parenthesis on both sides. So that's why you've got that double dot, or the double period for the multiline. And then the percentage sign 4.2f is telling you this is we want to output a floating point value in certain significant digits. This again is pretty standard output coding. You're welcome to look this up online. And then what we're outputting are the three outputs of heat solve 1, heat solve 2, and the mathematical result of the heat transfer, the radiative heat transfer, which would be 800 watts per square meter times 2 meters squared. Okay? And those are going to each sequentially be called out by the percentage sign. So you'll see that I have, in fact, 3 different percentage signs here, there, and there, that are assigned with heat solve 1, 2, and 3. Okay? And I'm just going through this to show you what's actually happening so that you could experiment with it and change it if you'd like to. So all of this work here is assuming that the surfaces are opaque, meaning the sky is opaque to long wave radiation effectively, and the flat plate collector certainly is opaque. So the transmittance is equal to 0, and then all the surfaces are assumed to be gray. They have a reflectance that is somewhere between 1 and 0. All right. That gets us past the how do we solve a problem. I'm going to let you work through the answer on that. But I want to go on to talk about the 4 different types of general gray body or selective surfaces for the opaque system. Because I think this is very important to have in your head and to understand the general notation that we use when we speak in terms of reflectance only. Okay, so if we look at our reading in Chapter 4, and I'm going to have you focus at page 74 to 77, and then the table of surface types are at the bottom of page 82 and the top of page 83. If we have a band from wavelength 1 to wavelength 2 that is equal to 0 for the transmittance, then I can represent my material surfaces using reflectance only. If the transmittance is 0, then the energy balance for the receiving surface is going to be rho plus alpha is equal to 1, or I reflect it as rho is equal to 1 minus alpha, and I have a nice little diagram there. If it is an emitting surface, then rho plus epsilon is equal to 1, and rho is going to be equal to 1 minus epsilon. The net balance, right, of course, is rho plus alpha plus tau is equal to 1, but we've driven tau to 0 in both cases because we have an opaque material. And then I just sketched out some diagrams to convey what direction the light is going in these two. So now I'm going to walk you through the 4 general material surfaces, the general cases that are going to be framed using what we would call a cutoff wavelength, or lambda c, which means this is just a breaking point at which the material is analyzed for either absorbing light or emitting light. And both alpha and epsilon from this use can be displayed in one plot. Well, effectively, only rho is going to be displayed, but we're going to be inferring both alpha and epsilon from our results. Consider that we separate the shortwave light coming in from the sun and the long wave light that is emitted from our terrestrial absorbers at about 3,000 nanometers. So we're going to use 3,000 nanometers as our cutoff wavelength. And now I'm drawing the first of our selective surfaces. Okay? We're going to have 2 types of selective surfaces and 2 types of gray bodies. A type 1 selective surface, you'll see that it has low reflectance in the shortwave band, wavelengths less than 3,000 nanometers, and high reflectance in the long wave band. A low reflectance in the shortwave band means a high alpha in the shortwave band. It means it's going to absorb that solar light, that solar radiation, very well. Meanwhile, the high rho in the long wave band means it's going to have a low emittance. It's not going to glow with long wave light very effectively. And I've drawn these, the alpha and the epsilon, in 2 different colors consistently as we go through so that you can see the differences, because this ends up holding quite a few things in your head. But you know, every time I see rho, it's going to mean the opposite value for either absorptance or emittance. That's a type 1 surface, and when I have something that absorbs light very well in the shortwave but does not glow long wave radiation very well, what I'm actually describing is a low E surface, or a low epsilon surface, and that's characterized by materials, real materials called metal suboxides, and this would be like chrome black or nickel black, conventional names for these. And they're great for the thin films of solar hot water collectors. So we have a great solar absorber, and it doesn't lose energy through radiative long wave losses. That's a great way to capture energy and maintain it for solar collector systems. We'll find that description on page 83. Okay. Now if I go to type 2 collector, I'm going to again have a selective surface. I'm going to have a type 2 collector, selective surface, and it's just going to be the opposite of what we'd drawn for a type 1. It's going to have a high reflectance in the short wave and a low reflectance in the long wave band. Now I'm going to take that reflectance term and I'm going to flip it for absorptance and emittance. So again, a high reflectance means a low absorptance in the short wave, and a low reflectance in the long wave means a high emittance. What do we have here? Well, we have a great white roof material. This is all the zinc oxides, titanium dioxides, magnesium oxides that would go into the paints and polymers for a diffuse reflector for cool roof technologies. So we have something that is a really good solar reflector, a diffuse reflector, and it's going to exhaust long wave radiation. It's going to dump long wave radiation out into the sky. So perfect for cool roofs. So, and this is just another way of pointing out that cool roofs are ultimately good solar design. We're just using the properties of the material as a selective surface. So now, that described our two selective surfaces. What do we get if the properties are uniformly gray for the material, and that, which there's no cutoff in the material? So I'm still going to draw a surface with a that has a cutoff wavelength in it, because the sun is dumping energy, shortwave energy, into us, and the surface that we have terrestrially will still emit loads of long wave energy out. So I'm still going to keep that, but the properties of the actual surface, the gray body, are uniformly gray. So it's I got a straight green line across there, and what I'm actually describing that has a high reflectance across all wavelengths is a spectral reflector, or a shiny metal. Pure gold, pure silver. It's going to reflect the shortwave light that's coming in, and it's also going to have a low emittance in the long wave. Right? High reflectance, low emittance. The type 2 gray body is going to be just the opposite. It's going to be uniformly dark, uniformly a low reflectance across all wavelengths. So high absorptance, high emittance, which is actually more of our classic carbon or soot materials, which is a near black body material. So if we want a real black body material, we pick carbon, soot, for that purpose. I want to remind you here that for all four of these plots, we've plotted reflectance, and we're inferring absorptance in the short wave and emittance in the long wave after that. Okay, so this does tie together. We're just using one type of plot instead of two, because both things are happening, and within solar energy design we really do need to think about tuning our materials to react to both the shortwave and the long wavelengths bands of light. And that wraps up our general understanding of shortwave and selective surfaces and gray bodies. Now I want to work an example for a selective surface. So we're going to assume that we have a selective surface that has a low reflectance in the short wave and a high reflectance in the long wave. And I'm going to have some givens here. I'm going to have that reflectance is going to be given a value of 0.1 in the short wave and 0.95 in the long wave. A cutoff again is going to be at 3 micrometers, which we can calculate for a fraction of the energy under the curve from those light sources using our code from Scilab. So if the sun is beating down on our surface, the sun is approximated as a 5,777 K surface, and I'm going to use that cutoff of 3 micrometers to give me a lambda T value of 17,331 micrometer Kelvin. Remember, that is our integrating factor, lambda T, not just lambda. And so from that, I can find a fraction of 0.979. So essentially, almost all of the energy under that curve is captured from the sun at 3 micrometers, 97.9%. Now I use that in my total balance of absorption or absorptance from the surface of this, from the material that I have, as say like the thin film of a solar hot water system. I'm going to absorb that shortwave energy, but I need to know alpha for the shortwave, like how much am I absorbing in the shortwave, and I'm going to need to know how much is under the curve of the light from the sun, the fraction of light coming in from the sun. And then I'm going to add to that the absorbed energy from the long wave times the other fraction. So you see here I've got alpha of the short wave is 1 minus 0.1 because the reflectance was 0.1, so alpha is equal to 1 minus the reflectance. Now I'm going to multiply that times 0.979. So I've got my first term for the total absorptance. Now let's work our way through the second term, which is going to be 1 minus 9.5 because of my reflectance balance. And the net remainder is going to be 1 minus 0.979. Add these guys together, and I'm going to get an absorptance of 0.88. If you break down those two terms, if you actually run out the math on the first term here versus the second term here, you're going to see that most of that contribution is going to come from the short wave, and very little of it is going to come from the long wave, which should make sense to you. But this is how we add together the ability of a real surface to absorb light from different bands of light. Now, that was the incoming energy. Let's imagine that same plate, that same thin film. It's going to be the same selective surface, but I'm going to flip the equation around and I'm going to think about emittance of light. So I'm just diagramming the same exact surface. I'm going to give you the same knowns, the same givens for the short wave and the long wave reflectance, the same cutoff of 3 micrometers or 3,000 nanometers. That would be the cutoff between the shortwave light band and the long wave band. But I'm going to think about that panel glowing. And the first thing I'm going to do is I'm going to estimate it glowing at 150 degrees Celsius. And let's see what the total emittance is going to be at 150 degrees Celsius or 423 Kelvin. So my lambda T in this case is going to give me 1,269, which will allow me to calculate a fraction from 0 to lambda T of 0.004. That's actually a very small value, so we're saying just a small portion of the energy is between is coming out in the band from 0 to lambda C, right? And so the emittance here is going to be 1 minus 0.0 for epsilon, excuse me, because we're using Kirchhoff's law along with this. And the 0.004 here is going to be the fraction of light under the curve from 0 to lambda T. And then I have my long wave component where we see that the vast majority of the long wave is coming in here. It's still going to give me an emittance of 0.05, which is fairly low. We knew this was a low emittance material. We also know that something glowing at 150 degrees Celsius is going to glow pretty much out here in the long wave. We're going to have very little energy glowing in the short wave, which was right here. This was the short wave, right? So most of the energy is glowing in the long wave, and even so, it's got a very low energy density, so the emittance is fairly low. Let's turn the temperature of that panel up. Let's turn the panel instead to 500 degrees, right? At a 500 degree panel, I'm going to run the same calculation, and what I get is a higher value of epsilon. And that's really because the fraction of energy under the curve is frankly higher. Now we have about 12.4%, whereas over here we had 0.4% contribution. Okay, it's just showing you that as I get hotter and hotter surface, the emittance gets more and more effective, such that until I have this, the sun itself, that's going to be a very high value. Okay? Worked example. Now, we have used this lecture to generate a complete idea of how we do gray body accounting for opaque surfaces. The next time we have a lecture, we will be dealing with semi-transparent surfaces. So what do we do when tau is not 0? And it's going to bring in the term reflectivity, R, as opposed to reflectance, rho. So keep an eye out for that, and we'll see you next lecture.